A very good morning to everyone. Today in this session we are going to discuss about the topic of learning vector quantization. In this topic, how the learning vector quantization is different from the other network in the sense means here we will be classifying the patterns where each output unit will be represents a class. So far we can say that LVQ is different from the vector quantization and coherent self-organizing maps. Basically it is a competitive network which uses the supervised learning. You all know about the supervised learning which I have discussed in the previous session. That is it used to learn through the training set. So based upon that they will be identifying the training set with the input provided, and then they try to achieve the target result, that is the desired output. So we may define the LVQ, that is an acronym which stands for linear vector quantization. It is a process of classifying the patterns where each output unit represents a class, and then it uses a supervised learning. The network will be a given set of training patterns with known classification along with the initial distribution of the output class. So once it completes the training process, the LVQ will classify an input vector by assigning it to the same class as that of the output unit. So this is the LVQ architecture. So how a network, artificial neural network will be? Here the same thing it used to follow, that is competitive learning is applied, that is a supervised learning is applied. So far what the input vector is applied at the input layer, the same kind of output will be expected at the output layer, and then we need to check that whether we are getting any deviation in the output or not. Because it is a supervised learning, we know that what the target output which we used to expect. So based upon that, when we make a comparison with the desired output which we got and then the targeted output, when we make a comparison, if there is any error or any deviations, what we need to do is we need to adjust the weight or the input parameters which we are giving at the input layer. We need to adjust it so that we can able to match the target output. So that's the criteria they are following in the LVQ architecture, so that in the network we are giving the different weights. The weight value will be varying. According to that, we can able to test the output of the LVQ network. So here the parameters used in the LVQ is for the training process of LVQ which we are using in the flow chart. These are the following parameters: X, T, W of j and then C of j, where X represents the training vector which varies from which is about from x1 and then x of I up to x of n, where T represents the class for training vector X, and then W of j is a weight vector for jth output unit. C of j is class associated with jth output unit. And then we are going to see now about the training algorithm for LVQ network. So how we are going to train our train the data sets, how we are going to train the input vectors based upon the desired output which we are going to get. So for that here we have some specialized training algorithm to be followed. So we have about the steps from 1 to 9 steps to be followed. At each step we will be doing some specific work to be done, iterated by the steps which is followed. So in the step 1, we need to initialize the reference vectors. What to be done? So after initializing the reference vectors, the step 1 is that we have divided the step 1 into again the 3 subcategories. Step 1A, that is step A, step B, and then step C. So from that, in step A, the given set of training vectors, take the first m number of clusters, that is the training vectors, and use them as a weight vectors. We need to use them as a weight vectors, and remaining can be used for the training. And then the next step B is we need to assign the initial weight and classification randomly. And then the step 3, we need to use a k-means clustering method. So this is the technique which you are used in the step 1. In step 2 is that we need to initialize the reference vector, that is alpha we need to initialize. And then in step 3, we need to continue with the steps 4 to 9 if the condition for stopping this algorithm is not met. So if the condition is not met, then we need to continue from step 4 to step 9. So if a condition we are meeting before with the step 4 itself, then we can stop it. Then the step 4, follow the steps 5 to 6 for every training input vector x. So we need to proceed to calculate the Euclidean distance, that is square of Euclidean distance, for j equal to 1 to m and I equal to 1 to m. So this is a formula to calculate the Euclidean distance. D of j equal to summation of I equal to 1 to n, and then summation of j equal to 1 to m, where x of I minus of w of ij the whole square. And then the step 6 is that obtain the winning unit j, where dj is minimum. So in the step 7, we need to calculate the new weight of the winning unit. So we in the step 6 we will be identifying the winning unit, and then in step 7 for the winning unit we need to identify the new weight. So to calculate the new weight, we have a formula. If t equal to c of j, then w of j of new equal to w of j of old plus alpha of x minus of w of j of old. So similarly, if t is not equal to c of j, then the formula is given. So in the first formula, instead of plus we need to put it as minus, then everything is the same formula. In step 8, we need to reduce the learning rate of alpha. So that's to be done in the step 8. In step 9, we need to test for the conditions. It may be follow as the maximum number of approaches reached, or the learning rate should be reduced to the negligible value. So care should be taken over this. Once if it reaches the maximum approach, or the learning rate is reduced to the negligible value. And then this is a flow chart which we used to follow. So whatever the steps which I have explained you in the training set, so that they have formed in the form of flow chart here. So first we need to start. So what the initial weight or the learning rate which you are going to select, that should be initialized, and then for that should be initialized for each input vector x, that should be in the decision box. If the condition is not satisfied, that is if the condition is true in the sense means, then the winning unit index of j we need to calculate it. Similarly, if the winning unit which you have obtained, we need to test with the formula. If t equal to c of j, then the corresponding formula. If t is not equal to c of j, if the condition is no, then the suitable formula should be applied. Then the reducing rate should be calculated by using that formula. So after this condition has reached, if it is reduced to the negligible value in the sense means, then we can stop it. If it is not reduced with the negligible value, then again we need to proceed to select the input vector. So this is about the linear vector quantization. I hope that you have been understood the concepts clearly about the LVQ. And then we have the variants over the LVQ. What are those? Are LVQ2 and then LVQ 2.1 and LVQ3 have been developed by Kohonen. So these are the versions or flavors of LVQ. So however, the complexity in all these three variants are due to the concept that a winner as well as the runner-up unit will learn is more than in LVQ, which means that here whatever we are giving the input vectors, whoever winning will be, succeeding will be going to the next step. So that's what happening here. So over this three variants also, the complexity will be analyzed based upon that who is a winner and then who is a runner will be learning it. So those who have been loose, they are not going to proceed with the next step. So that's what they are concluding here. I hope that you have been clear about the concepts of LVQ. Thank you.